There's a famous story where Isaac Newton was sitting under a tree and an apple fell down. And when this apple fell, he saw it and he asked the greatest question ever asked by humans. If the apple falls from the tree, why does the moon in the sky not fall either? And this led to him developing Newton's law of universal gravitation, which I'll help you understand right now. Imagine if you and the earth that you're standing on, is connected by an invisible rope. This rope pulls you toward Earth and pulls Earth toward you. This invisible rope is called gravity. Now imagine that every particle in the universe, every star, every planet, every moon, every animal, every particle, everything is connected by these ropes. That is Newton's law of universal gravitation, that everything is acting on each other with gravity. Everything is pulling toward each other in some way, no matter how minuscule. So his law in equation form is F equals G m1 m2 over r squared. Let's break this down. This G is called the universal gravitational constant, and it's a super precise, super important number, because if it was too small, everything would fall apart, we wouldn't exist. If it was too big, everything would implode. This means the force of gravity, so let's write this out. M1 and M2 just means the mass of the two objects, and the radius is the distance between them. By the way, here's the accepted value for the gravitational constant. Now, of course, you don't have to memorize this or anything, and it's some cool science. Let's go through a fun example. Do two dogs attract each other gravitationally? Let's have dog 1, let's draw him, so doggy. And dog 1 is 10 kilos. Dog number 2, so his new friend that he met at the park, he's not very happy, he's sad. And dog 2 is 20 kilos, he's quite a bit fatter. They are sitting 0.5 meters apart from each other. How strong are they attracting each other gravitationally? Let's check with Newton's law of gravitation. Now here's something interesting. This is called forces acting at a distance, because before Newton came up with this idea, we thought forces were all exerted by some other force, like you pulling open your door, or you lifting up an object. People had some trouble accepting the idea of two objects acting on each other with forces without touching. So forces at a distance like gravity are called non-contact forces. Anyway, moving on with the solving. We just have to substitute everything in. I'm going to speed it up because it's some big numbers. This is roughly 5.04 times 10 to the negative 8 newtons. This number is so small that it's unnoticeable. You cannot notice these two dogs attracting each other. And even if you did care about this tiny force, usually the force like friction and tension in muscles is way stronger. So this gravitational attraction between these two doggies is impossible to see. Here's a cool space example. This is Earth, alright? And this is the radius of Earth. Let's say you have a satellite and it's 2 radii away, which means that your satellite is twice the radius of Earth away in distance. So if this is radius of Earth, then this is 2 times radius of Earth. Your satellite is spinning around in orbit and it weighs 4,600 kilos. To find how strong gravity is acting on each other here, we could use the law. But let me introduce you a concept called the inverse square law. So as we know, the law of gravitation says this. Mass 1, mass 2 times g divided by radius squared. This means that as you get further and further away from Earth or any object, the gravitational force you experience decreases by the square of your distance. Now, the force of gravity at the surface of Earth is mg, that's our weight. And our satellite is twice as far, which means that because of the inverse square law, it would be 1 over 2 squared times mg, which is 1 over 4 mg. That means the satellite experiences a quarter of the weight that we experience on the surface of Earth. If you went through and did this calculation, you get 11270 newtons. That's the amount of force gravity is pulling on it. By the way, something that really helps me is having all the formulas you ever need in one place. And I make these cheat sheets for myself, and if you want your own, it's in the description for free. So go sign up.